introduction. Alexander Thomas is an associate professor of mathematics at the University of Lyon. He works broadly in the area of geometry, quantum algebra, and mathematical physics. And he runs the popular YouTube channel Thomas, which makes math accessible at various math at various levels accessible to all. They're beautifully produced videos that are in French, and I would recommend them to you especially if you like listening to math in French. So now I'm going to hand it over to Alexander. Thank you so much.
Yeah, thanks. Thank you a lot for the invitation. And it's really a lovely community. I discovered this community recently at the IHP. So yeah, I'm really happy to share my work. So I will share my screen. And here we go. Yeah, so my talk will be about fractions and how to visualize fractions. Part of the story is well known, especially the beginning. I think most of you will know. But then the second part has to be new because it's really work in progress. So let's start with a very simple question, which might even seem to be stupid, like how to represent actually a number, say in a graphical way. Well, probably you would say, well, real numbers all lie on the line. So you just have a number finally is a point on the real line. But then you can ask, well, is it the only way to represent numbers? Well, probably not, right? There are probably many ways to represent numbers, but are there like interesting ways? And one way was proposed by Lester Ford, in 1938. And his proposal is to say, well, let's just speak about fractions. And to him, a rational number is a circle, not a point, it's a circle. So it's a circle which lives above the real axis, and the circle associated to the rational number p over q, well, it's a circle which touches the real line at this point, at p over q, and its radius is given by this kind of magical formula, 1 over 2q squared. So let's see what this gives. Like if you just take an integer, well, an integer, its denominator is 1, so its radius is 1/2. And you already see that these circles, well, they patch nicely together. What happens to 1/2? Well, 1/2 denominator is 2, so the radius will be 1 over 8. And actually it happens that it's exactly the circle which somehow fits into this triangle. And actually it keeps going. Like when you do this simple construction, doing a circle, like putting these 4 circles for all rational numbers, you get this beautiful picture. Where these circles, they never overlap. They are at most tangent. You can also reverse somehow this process. You can also start with these circles, like these big circles, and then just fill in these kind of triangles. So you fill them in, and then you fill in again. And then somehow the statement is that the set of all contact points is exactly the set of rational numbers, which is not obvious. And also, 2 rational numbers, like their 4th circles, they will be tangent if and only if this kind of condition, kind of determinant condition is satisfied, ps minus rq equals to 1. And in that case, so when 2 rational numbers somehow see each other somehow through these circles, then again, there's a kind of a unique 3rd circle you can add in the middle, and its contact point has a very nice formula. It's a plus c over b plus d. So this is called the Fourier addition. So somehow you can start actually from the integers, or actually just from 0 and 1. And then using this Fourier addition, somehow you can construct all the rational numbers. Okay, so now we have like a first visualization of rational numbers. But you might ask, well, what's this useful? Why is this way of visualizing rational numbers interesting? But actually, there's a very nice application to the theory of approximation, especially when you have an irrational number and you try to approximate it. So let's take, for example, pi. Well, one way, of course, of approximating a number is just simply you write it in decimals and then you cut at some point. So like pi, here I took 6 decimals, I think, after the comma. And so, yeah, you get some approximation. But maybe you already see that this fraction is pretty big. You can actually get the same 6 digits with a much, much smaller fraction. You can just take this 355 over 113. You see, it's much, much smaller. You get the same number of digits. So you might ask, well, but how do I find these kind of good approximations, these kind of denominators which work well? And do they actually exist? This is kind of classical theorem from the 19th century, probably due to Dirichlet, Hurwitz, and many others, which tells you the following: for every irrational number, there are infinitely many rationals which have this kind of quadratic approximation property. If you try to just prove it like this, actually it's pretty hard. But using the fourth circles, it's almost obvious, this theorem. So here's the proof. So you take your fourth circles, this kind of fractal, you take your irrational alpha somewhere on the real line, represented as a point, and you draw this vertical line. So you can imagine that somehow you travel on this red line coming from above, and you go towards alpha. But since these circles somehow they cover the space above the real line, you will somehow enter in a circle, then go out, enter another circle, go out. Finally, you will visit an infinite number of these fourth circles. And whenever you enter a fourth circle, well, actually, by definition, your distance between alpha and the associated rational number is smaller than the radius. But the radius of the fourth circle is 1 over denominator squared. So you have the proof of your theorem. Okay, so in order to go to somehow the second visualization I want to present you, how to visualize rationals, I will come back to just this picture of the fourth circles. So here I added one more line, this horizontal line, which actually is also a fourth circle associated to infinity. Somehow infinity is like 1 over 0. It's actually also a rational number. So of course, its fourth circle is the straight line. And so now somehow we will shift a little bit perspective and we will really consider this picture as living in the upper half space. And the upper half space is a model of hyperbolic plane. So in the hyperbolic plane, these circles which are tangent to the real line, actually they are horocycles. And when you have horocycles, it's kind of natural to consider geodesics, the geodesics which link them. So that's what we will do. Whenever two horocycles are tangent, which means that their associated rational numbers satisfy this determinant property, well, then I will just draw the geodesic between these rationals. In the hyperbolic plane, a geodesic is this kind of half circle. And actually it turns out that this half circle will even go through the contact point. And so I will draw all of these lines, like at many of these curved lines, and I will also get some vertical lines, which are actually the geodesics between integers and infinity. So once I do this, actually I can forget about the fourth circles. And what I see is simply a triangulation, the famous Farey triangulation of hyperbolic plane. So maybe it's easier to draw this picture in another model, in the Poincaré disk model, because then you somehow see a bit more easily why it's a triangulation. And so again, the set of vertices of this triangulation is exactly the set of rationals and infinity. So now you might wonder what's actually the symmetry of this picture. There's actually a lot of symmetry. Well, for example, you see that's kind of symmetric with respect to the midpoint. Let's take a rotation by an angle of pi. But you actually also have another symmetry, which is around this red dot, which is the midpoint of this triangle. Well, it's a hyperbolic picture, so it's really about hyperbolic geometry, like hyperbolic symmetries. And well, these symmetries, they act by isometries. And the isometry group of hyperbolic plane is like SL2R, PSL2R. But here we have a discrete subgroup, and this subgroup is actually the modular group. So the modular group, it has these two generators. So S, which is exactly this rotation around the green dot. It's a rotation around I, hyperbolic rotation around I by angle pi. And then you have this other element of order 3, which is kind of this rotation around the red dot, rotation by an angle 2 pi over 3. And well, it turns out that it's actually a composition of T and S, T being this matrix. So when I write a matrix here, it's actually really a matrix of a Möbius transformation. So it's a transformation which is linear fractional. So T actually is simply a shift. It sends Z to Z plus 1. So in this picture, Z would somehow turn this picture. It's like a parabolic transformation around infinity. Okay, and S, yeah, by the way, S has this nice formula. It actually sends Z to minus 1 over Z. So it has this kind of 2 by 2 matrix representative. Okay, so am I telling you all this? So somehow the idea now is you take this picture, this Fourier triangulation, you have its symmetry, and now we will actually deform the symmetry and then ask how do we deform the picture. So this was done actually quite recently, in around 2020, by two French mathematicians, Sophie Mourier-Genoux and Valentin Ovsienko. So what they did is they somehow took these two matrices, so these generators of the modular group, and they figured out that you can actually deform them. So they introduced this kind of formal parameter Q, and they consider these two matrices. So very explicit. So you should again think about them as Möbius transformations. And what they noticed is that these two deformed matrices, they satisfy the same relations. SQ squared is 1, and the product TQ to the power of 3 is 1 as well. So this means that the group generated by TQ and SQ is really nothing else than the modular group. The group itself stays the same. But what changes is kind of its action, how it acts on the hyperbolic plane. And so now you might ask, okay, so for the usual modular group, by the way, you recover the usual modular group for Q equals 1. So for Q equals 1, somehow this modular group is the symmetry of the Fourier triangulation. So what is kind of the geometric picture for this deformed representation? And so this is like joint work with Perrine Jouter and Olga Paris-Romaskevich, in which somehow we answer this question. And well, the answer is the following picture. I just show you the picture. So it's of course not the full triangulation, but probably you get the idea. Somehow initially we had a triangle between 0, 1, and infinity. It was an ideal triangle, so it was all these 3 points were on the boundary. And now when you turn on somehow your parameter Q, then these ideal points actually they will open up. So from a Euclidean perspective, you might say, well, now we have actually a hexagon. But somehow from the hyperbolic perspective, it's more like an hyper-ideal triangle. Or if you prefer, like before you had a cusp, like 2 points, two geodesics coming together at infinity, it's a cusp. And now you open up the cusp, and hyperbolically what happens is you get a funnel, something which becomes smaller, and then it becomes bigger again, and actually it becomes exponentially bigger. So all these cusps open up, but still, like when you do the triangulation, you actually just reflect with respect to the sides, and this you can still do. So you get kind of this tessellation of the hyperbolic plane with these kind of opened up triangles. And the interesting thing now is that initially we had all these rational numbers, which were the vertices, but all these vertices now they somehow open up and they become kind of an interval. So we can associate an interval to every rational number. And what's amazing kind of is that all these intervals, they are still well organized and they never overlap. There's an interval for every rational number. And somehow, since it comes from a discrete faithful group action, they will be nicely ordered. So the way we think about it is slightly different. So first of all, let's put it in the upper half plane model. In the upper half plane model, well, the boundary is just a real line. So what I showed earlier was kind of an interval. I said for every rational number, you should think you can associate an interval. But in the hyperbolic plane, it's kind of natural to consider the geodesic between these 2 points. And then I just reflect, and what I get is a circle. So somehow the second picture I want to somehow convey today is you should maybe think about a rational number as a circle, but not a circle like a fourth circle which lives above the real axis. It's a circle which lives like inside the real axis, orthogonal to it. Well, and you might say, well, but how is this possible actually? Like rational numbers, they are already dense, they are already everywhere. How can you somehow thicken them without like, yeah, eating each other? Or like, how is it possible that all these disks are disjoint? Seems to be impossible. Somehow, the point is that a rational number, when it gets deformed, so when you turn on your parameter, the interval or the disk you get does not necessarily contain the rational number. It might move somewhere else. So you should really think about this as follows. So the circle, as you see here, for example, it corresponds to some number, say -1. Somewhere else you have another circle which corresponds to 1. Since these circles are completely disjoint, there is enough space in the middle to put somewhere a 0. And then you keep going. Between 0 and 1, there's enough space to put 1/2. And between -1 and 0, you have -1/2, and so on and so on. So somehow from this perspective, it's a bit like constructing Cantor set. So you see that it is actually possible to associate a disk to each rational number and they will not overlap. So really in this picture, the disks, they never overlap and they're not even tangent. They're always strictly disjoint. So that's the second picture I wanted to show. But it has actually a nice feature, which is kind of very different from the fourth circles, which is that the fourth circles, it's kind of a static picture. It's just one picture. But here we have actually a whole family of pictures. We have this parameter. We can move it. It's kind of it's more like a video. It's more like an animation. And in particular, it means that there is actually kind of an explicit formula for all these points, like all these intersection points of all the disks with the real axis. They have a formula. They have a precise formula in terms of this parameter q. For example, the disk which is associated to 1 is always the disk with diameter between q and 1. And yeah, if you take -1, for example, it's always the disk of diameter between -1 over q squared and -1 over q. So here, in particular, you see that -1 is not necessarily part of this interval. Okay, so here it's maybe time to show you some shader where you can really see this, yeah, in action. So let's go here. I hope you see the screen. Yes, you should see the screen. So this is an animation which, well, has two parameters. One parameter is, well, Q, and the other parameter is just zoom. So when I clicked here, I'm somehow with parameter Q equals to 1. So Q equals to 1 means the usual picture. So what you see here actually is kind of a Fourier triangulation, of kind of refined version of the Fourier triangulation. So what I will do, I will turn on the parameter. When I turn on the parameter, you will see all these kind of pearls which grow. These are the disks. The disk here in the middle is 0. Then you have 1, 2, 3. Between 0 and 1, you have 1/2, 1/3, 1/4, etc. So like, yeah, every rational number appears. What is this huge block over here? This huge black block. It's also a circle. It's a circle which is infinitely large. Well, you can just count. This is 0, 1, 2, 3, 4, 5, 6, 7, 8. Actually, this infinite block is infinity. It's infinity. And just to be sure that we are not missing anything, we can zoom in. We can zoom in and we will see that there will be circles again and again and again. So we really see kind of the complexity of this image. Between any two disks, there are infinitely many more disks, because between any two rational numbers, you have infinitely many more. So you can, yeah, you can play around. Things will get bigger, smaller. Yeah. Okay, I think you got the idea. Let's go back to the slides. So this is kind of the second visualization. So again, you should ask, what's good for? What is it good for? And the answer is actually really, it came from some experimental math. Really, it's a property we found really through visualization. When you have two circles, which are distant, then there are two special points, which are called the homothency centers. What you do is just draw the common tangents. So you have two inner tangents and two outer tangents. They intersect in 2 points. And what we observed with Perrine and Olga is that actually very often when you consider these homothency centers, they lie again on another circle in our kind of circle necklace. To be more precise, when you take a pair of Q disks associated to Furry neighbors, so Furry neighbors just means that this determinant AD minus BC equals 1, then the inner and outer homothency center lies again on a Q disk. And actually, it's more precise than this. The inner one is always to the right of a disk, and the outer one is always to the left. And so now you might ask, well, what's the formula? What is the rational number associated to these? Maybe you might guess, probably it's again the Fourier addition. Well, this is wrong. The formula is as follows. It's kind of a Fourier addition, but it's different. It's actually a quadratic version, kind of a quadratic version of the Fourier operation. So what you do is somehow you take this A over B and you multiply numerator and denominator by B. You make it bigger, AB over B squared. Again, the same for the other ones, CD over D squared, and then you add them up. Kind of curious, right? So we coined this operation the Springborn operation because in some other work by Boris Springborn, he actually introduced these quite recently in a completely different context, more like a context of Diophantine approximation. But it's kind of still linked, right, to the fourth circles in particular. So now you could actually say, well, you start from, say, integers. You have this Springborn operation, and you can build all your rational numbers. Okay, so this is kind of the second visualization of rational numbers. And so now I want to go on a little bit and ask the following question. Can we do actually more than rational numbers? So especially when you have this kind of picture of all these Q disks, it's kind of a necklace, right? You have kind of the real axis as a necklace and all these pearls on it. Well, it really feels like maybe it's possible to fill the whole plane, to add more disks outside the real line. Well, and then what should these circles, these disks correspond to? They should correspond to some complex number, right? So somehow the question becomes, yeah, can we Q deform complex numbers? So just to give you an artistic like thing, we try to find is a picture like this. This is like a picture from the Fomenko book on mathematical impressions. So we are looking somehow, we try to find a fractal, a 2D fractal, just out of circles, which looks like this, such that each circle corresponds to some number. So on the real line, we had all these rational numbers. So you might ask, okay, what's outside? What is a complex analog of a rational number? Well, easy guess would be just a plus bi with a and b rational. It turns out that there is actually a better choice, which is a plus bi square root of 3. Why? So what you can do, what I draw here is just the integer letters. For each of these quadratic fields, you can draw the integer letters. So for a plus bi, you just have square letters. But for a plus bi square root of 3, you have this lattice with equilateral triangles. So first reason would be to say that actually equilateral triangle has more symmetries. This picture on the right has more symmetries than the picture on the left. But there's actually another reason, which is even better, which comes again from hyperbolic geometry. It comes from the 3D analog of the Fourier tessellation. So the Fourier tessellation, you have like this disk and you have a triangulation. So the 3D analog is the ball model, hyperbolic 3 space. And it actually turns out that you can tessellate it with regular ideal tetrahedra. And if you just compute the set of vertices of this tessellation, it turns out that it is this quadratic field Q adjoint I square root of 3 and infinity. So this is somehow why it's kind of natural to consider rational complex numbers as being elements of this field. But actually, there's a really major difficulty with complex numbers. And it comes from Mostow rigidity. So for those who know a little bit about hyperbolic 2 and 3D geometry, you probably know this. So in 2D hyperbolic geometry, you can deform a lot of stuff. But whenever you have hyperbolic 3 space, or even higher dimensions, then many groups or many lattices, you cannot deform them anymore. So somehow the natural thing we would like to do, taking some symmetry group, which is like analogous to the modular group, which is called the Bianchi group, you cannot deform it. So somehow the idea we had is to take hyperbolic 3 space and to slice it, just cut it by planes. And on every plane, well, on every cut, we have a hyperbolic plane now, and on this hyperbolic plane, we can deform. And then we try somehow to stack things together. And so here is where more shaders will come. So we have already seen the real numbers. So let's see the pure imaginary numbers. You see, it's a picture which is pretty similar to the picture before. We should just turn your head. It seems like the previous picture. Now it's the real, it's the imaginary axis. Actually, if you're very precise, you will actually see it's slightly different because the basic distance on the real axis was between 0 and 1. But here on the imaginary axis, the basic distance now is between 0 and I square root of 3. So actually, somehow the unit is not 1, but square root of 3. And this changes actually. So the symmetry group of this picture here is not the modular group. It's some Hecke group. It's called the Hecke 6 group. But the Hecke 6 group, you can actually deform it pretty the same way as you can deform the modular group. So I can turn on the parameter, you get the deformation. But there's one new feature is that the imaginary axis itself will actually deform. It does not stay straight. It becomes itself actually a circle. That's why you should really think about it as a necklace. And so along this necklace, you have, again, all these pearls representing all all complex numbers of the form rational number times I square root of 3. So, yeah. So somehow when you have hyperbolic 3 space, you can cut it along the equator, you get real axis. You can cut it orthogonally, you get the imaginary axis. This is this picture. And then there's a third way to cut, which corresponds to the unit circle. So this is the third shader I want to show you, the unit circle. So on this unit circle, again, you have some kind of symmetry group, which is a bit more complicated. It's a Coxeter group. And again, this Coxeter group, you can deform it. You can look at what happens to the picture. And you still see the unit circle, but again, you have all these pearls. And these pearls now corresponds to complex numbers of the form a plus b I square root of 3, which lie on the unit circle. You can go out, you can go in. So these are these kind of slices I talked about. So now you can just superpose them. You just take all of them together. You get to this picture. Yes, you see kind of unit circle and the two axes. And now I can turn on the parameter. And you see all these three slices, they nicely fit together. And actually you can check, for example, the unit circle intersects the real axis along 1 and -1. So these are represented by some circles. But there is kind of this intersection here between the imaginary axis and the unit circle. This is I and minus I. But I is not in our field. So this means that it's just a point. And this is actually what I can do. I can zoom in. And indeed, I is just a point. And you see in particular that these two necklaces, they nicely stay apart one from each other. Great. And then there's a final thing. So here I somehow just have these three necklaces, one next to each other. It's kind of like from the computer perspective, you just take the union of the three programs. But what you can do is actually you can, instead of having one program added to another, you can actually put one program inside another and somehow impose a global symmetry by the modular group. And what happens then is you get this amazing picture, which was on the poster. So here again, we are at q equals 1, so no deformation. So you already see there's a lot of stuff happening on this picture. So now if I turn on the parameter, there are all these pearls appearing, and you can still somehow see there's the real axis in the middle, somewhere there's the imaginary axis, which is a bit curved, somewhere you should have the unit circle somewhere here. But actually what happens is like you draw the Fourier tessellation, and for each arc is replaced by this infinite circle necklace, this fractal along this necklace. Yeah, so now you can play with this picture. You can zoom in. You see there's a lot of stuff. Well, you might still see that there's still space. There's still some regions where we don't have circles. It's not like that the computer is not computing enough. It's really there really is circles missing. And for now, we don't really know how to fill this in. It's really a work in progress, how to fill in these spaces. But one really interesting thing you can notice is when I go with my parameter towards 0, it's like one of the degenerations, so we have to move you. One of the ways to degenerate this picture is actually to go to q equals 0, and what happens is that it converges to this picture, probably many of you recognize. It's actually the Apollonian fractal. The Apollonian fractal in the kind of band model. And of course, you see that there are a lot of circles missing. But somehow we are kind of confident to be able someday to fill in these gaps. Like all these gaps, we hope that we will fill them, in particular because of this reason that we know how to fill in this picture. So somehow you can start from the Apollonian fractal and try to somehow deform it in a certain way. Okay, I have maybe 2 or 3 minutes left, so I can show you one more picture, and you can ask your questions. I have one more picture, and I will ask you whether you see the difference. Let's go to q equals 0. So this is like the starting point. I don't know if you can already see a difference. Like before, it was pretty similar. I can turn it on. I don't know if you get it. So the difference is that before we had all these equilateral triangles. Like the big black dots, they formed equilateral triangles. This is why we had the square root of 3, because the square root of 3 is kind of the height of an equilateral triangle. Here you don't see triangles, you see more like these rectangles. So actually what this picture is, it's not q adjoint I square root of 3, it's q adjoint I square root of 2. So for some reason, so somehow I argued why it's very important to use square root of 3. For some reason, actually, you can also use square root of 2. And yeah, so you get pretty much the same picture. You can zoom in. You have all these disks. But there's kind of one new feature, which is that there is this point here I'm zooming into, where now 3 necklaces will come together. Actually, in the previous picture, at this point precisely, there was actually a disk. But now this point does not belong to our field anymore. So yeah, you have these necklaces coming together. And again, you see that all these circles, they nicely behave. They never overlap. And another thing we should have a look at is when the parameter goes to 0. the parameter goes to 0, well, you again have kind of a degeneration, and it will degenerate to this picture, which maybe you might recognize, maybe not. It's also a Apollonian kind of fractal, but the Apollonian fractal somehow is related to the tetrahedron. This picture is related to the octahedron. So yeah, so you get the octahedral Apollonian fractal. And again, so somehow we know how this picture should look like. So we hope that we can at some point be able to fill in this picture. Okay, I think that's all I wanted to tell you. And hope you enjoyed. And yeah, don't hesitate to ask your questions.
Amazing. Thank you so much. I think now we can be open for questions. If folks want to type in questions, I can flash them, or if people want to raise their hands. We have a couple raised hands. Um, Aaron, I think, was the first one.
Yeah, very cool talk. I had a couple of questions. The first one was, so in the initial picture you showed where you just do the Q deformation, if am I understanding correctly that by using the you know, path of triangles or like geodesic representation of irrationals, this also gives you a deformation of the irrational numbers?
Yeah, actually, that's a good question. Like irrational numbers, what happens to them? Well, they stay points. They stay points. So somehow you can ask, what is the function which to an irrational x associates xq somehow?
Yeah.
And this is a non-trivial question. Like in this work by Moret-Genoux and Ovsienko, they somehow show that you can Taylor expand. It's an analytic function for q being near 0. But they
Huh.
prove somehow that that the radius of convergence is finite. It's pretty small. It's like, I don't know, something like golden ratio or something. But somehow from this geometric perspective, it's pretty clear that this function exists for all q.
Right.
So you should ask, like, yeah, how can you actually analytically continue their expressions? And there's also been some very recent work by Pavel Itengov, who somehow considered this function not for real q, but for complex q. And he actually finds some region in which this function for irrationals converge. It looks like a raindrop. But yeah, actually, you can somehow extend this raindrop along the real axis. But I don't know if I think for a generic irrational number, there's no known formula. For some, like especially for quadratic irrationals, you can explicitly write down a closed formula, some quadratic expression in like this, some square root. Yeah.
Yeah.
You
But
can do it for
since,
some irrationals. I
yeah.
don't know what more.
But like looking at the picture, it seems clear that the function is order preserving and it has
Yes.
gaps when q is less than 1. So should I think this is like some sort of Cantor type function?
So now you're speaking about what function are you speaking of? Like if you fix x and you vary q, this should be a continuous function. If you fix
Uh,
q and you vary
very
x,
X. Yeah.
if you fix q and you vary x, yeah, then you have a function which is only continuous at the irrationals
Right.
and which is discontinuous at the rationals, and the discontinuity is exactly the diameter of these
Yeah.
disks. Yeah.
Yeah. And you can compute it, presumably you can compute it explicitly by using the continued fraction expansion, you know, the same
Yes. Yeah, there's an
continued fraction
explicit
expansion, but
formula.
with the
Yeah,
different matrices or different Mobius transforms. Awesome.
exactly. Yeah.
Thanks so much. Yeah, that's very cool.
You're welcome.
I'm going to flash a couple from the chat. I think Vladimir asked if you could share links to your shaders, and Jim asked if you could share links to your archive links to your papers. So if you have time to do that on the chat or at the Discord, I think folks would love to see that. And I see that Jim is raising his hand, so I'll let Jim ask a question now.
Yeah, is there any connection with Ford spheres?
Mm, well, fourth spheres, they are horospheres in the hyperbolic 3 space, but somehow, I mean, of course, the picture I show you, like for example, what is still on the screen, it is a picture of what happens at infinity of hyperbolic 3 space. So infinity is like C or CP1, like C with point at infinity. So well, the fourth spheres, like if you would draw what they do at infinity, they just touch, right? You just have a point. So, yeah, so I don't know. Actually, I don't think that there's a direct link. One thing I can say is the following. If you just consider the rationals, just this one-dimensional thing, so there's kind of this big difference, right? The fourth circle lives above, and our circles live somehow inside the real axis. What you can do, you can take a Taylor development when Q is close to 1. So when Q is close to 1, all these disks, they're almost points. And if you consider the diameter or the radius of, consider the radius of a disk which corresponds to A over B, well, it's actually Q minus 1 times the radius of the fourth circle, 1 over 2b squared. Means somehow that, well, when you take Q close to 1 and you somehow rescale the picture, then actually you see somehow a fourth circle. But still, yeah, I think there are maybe more links between the fourth circles and this picture than we know at the moment. But yeah, I think that's all what I can say.
Cool. I'll flash one more question from the chat, which was from Scott Borthman, who asked, is there a reason not to try Q I root 5? And I would say more generally, like, is there a framework where you could do something like this for quadratic imaginary fields?
Well, of course, we try, but actually, quadratic imaginary fields, they have strange properties. They're like, yeah, some of them are Euclidean, many of them are not. I mean, there's a finite list of Euclidean rings. I mean, what I want to say is like if you take the integer ring, then very often it's not Euclidean. And somehow doing these kind of circle packings, very often it's linked to some kind of Euclidean algorithm. So we have some hope to do it for Q adjoint, well, I squared of 2, 3, 7, and 11. These are like the 5 cases where the integers of these fields are Euclidean. But for now, we don't really know. We don't know. And in particular, what I tried is, well, in this limit, when Q goes to 0, we had like the Apollonian fractal, which is kind of a tetrahedron. We had this kind of octahedron. So the next thing would be the icosahedron, which exists, like the Apollonian fractal of icosahedral type exists. So I tried like to find like a way to get this picture. And in particular, I tried for Q adjoint I square root of 5, because somehow square root of 5 appears a lot in the icosahedron. But yeah, I failed. I mean, I can show you actually the picture. Where is it? Here in the shaders. I have a shader for Q adjoint square root of 5. Oh, okay. Sorry, this would take some time. And the picture looks pretty nice, but at some point, something bad happens. Oh yeah, it's compiling. I don't know why, but this one compiles for longer than the others. So the thing which happens is like we really want all these disks to be disjoint. Somehow every disk should represent a number, and numbers, they are different. And what happens in this shader I have here, if it compiles, is that at some point, some of these disks will overlap. Oh yeah, here we go. So here we have the picture. So, well, just the colors are a bit different. Yeah, so it's pretty much the same thing as usual. You have this rectangle because you have square root of 5 now. And it seems actually that everything goes well, but if you zoom in, this is, well, one of these special
can't see it.
points of order 3.
We can't see it.
If you move, you can't see it?
I can see it.
Oh, I hope that everybody can see it. Well, but probably, well, what happens is that these disks, they will merge, and then, yeah, like all these things, they are not avoiding each other. Well, maybe it's just, it means that I did not use the good field, or maybe I did not use the correct formulas. It's also some guessing sometimes. But yeah, so for now, we can't, we don't know. But we would love to do it for every quadratic imaginary field. Yes.
Great. I know it is after time, but I think I'm not the only person dying to hear Kate's question. So I'm gonna let Kate ask one more question before we sign off.
Thanks, Gabe. My question was just so you explained that sort of the last step you had performed was to use the fairy tessellation on the real line to reflect all of the necklaces you already had to get more necklaces. And so the natural question is there's an analog for the Hecke group on the imaginary line, right? A tessellation. You could do that instead or as well. And I'm just curious what happens.
Yeah, it's a very good question, a very good point. I mean, if you do it simultaneously, then things will overlap, so it's somehow incompatible. But we are about to think about it. What happens if you somehow only impose one of these, like for example, the symmetry you have on the imaginary axis? Initially, I thought that this does not work, but now I think we did something wrong some weeks ago. I think we can do it, but yeah, we have to figure this out. It might be possible that you can have like a global symmetry by this Hecke group and just having kind of a local symmetry along the real axis, which is the modular group. Might be possible, but yeah, I'm not completely sure now.
Thank you.
Great. Thank you so much. Thanks, Alex, for a wonderful talk. Thank you also to Carolyn and Juliet. This was an amazing session. What a great way to spend a hot June day. I will hand it off to Aaron to close us out.
I guess we are concluding for the day here. Thanks again to all the speakers. Thank you all for coming. Remember to check out the exhibit in Paris if you're there. Once again, our summer break is beginning, so we'll not meet next month, July or August. And I guess we haven't talked about resuming, but I think we'll probably resume in September is my guess. So stay tuned. Enjoy the Northern Hemisphere's summer. And we will stop the recording and sign off now. Thanks, everybody.